Howdy, my name's Georgi Farouk, and this is my self-study assignment. So in this presentation, we're going to talk about Bode plots, gain phase margins, phase lead lag, and lead lag compensators, as well as the Nyquist stability criteria. So starting with Bode plots represent the frequency of a system or the behavior of the system at different frequencies using two different plots, a magnitude plot, which plots the gain versus the frequency, and a phase plot, which plots the phase angle versus the frequency. To draw a Bode plot, you need to find the poles and zeros of the transfer function, identify the corner frequencies, sketch the magnitude plot, starting with the initial DC gain, and then with each pole adding either negative 20 dB, and with each zero adding positive 20 dB. And the phase plot shifts the phase by plus or minus 90 degrees over 2 decades. So as an example, we're going to use the function 100 over s plus 2 times s plus 5. So here we can see that the poles are at s equals -2 and -5, with the corner frequencies being 2 and 5 radians. So we know that the initial magnitude is 100, so 20 times the log base 10 of 100 is 40 dB. After 2 radians, the slope will drop by 20 dB, and after 5 radians, it'll drop by another 20 dB. The phase plot shifts the phase by plus or minus 90 degrees over 2 decades, and we can see what that would look like in these two graphs. So gain and phase margins. The gain margin of a system is how much gain it can tolerate before it becomes unstable, and it's measured at the phase crossover period where the phase is negative 180 degrees. The phase margin of a system is how much phase lag it can tolerate before becoming unstable, and is measured at the gain crossover frequency where the magnitude is at 0 dB. So to calculate this, you plot the Bode plot of your transfer function, you find the gain crossover frequencies, and then you calculate the phase margin using the equation PM equals 180 plus the phase at omega GC. And then you find the phase crossover frequency and calculate the gain margin. So using the same example as in the previous slides, we can see that the Bode plot magnitude starts at 40 dB and changes when the frequency is at 2 and 5 radians per second. Through this, we can find that the gain margin is at 10 dB at 3 radians per second and 45 degrees at 2 radians per second. This means that the system is stable because both these values are positive, and that the system can tolerate a 10 dB increase in gain and 45 degrees before becoming unstable. So here are the Bode plots for that. I marked the intersections with red. So a phase lead compensator is something that adds positive phase to a system, which, depending on the application, can improve phase bandwidth, margin, and stability. The formula is D of S equals K times S plus Z over S plus P, where Z is the pole additive and Z is the zero additive and P is the pole additive, assuming that Z is less than P. To calculate this, you identify the desired phase margin increase that you want to get. You determine the required phase lead. You place a 0 and pole to achieve a boost near the crossover frequency, and then you adjust K to set the gain crossover. So in this example, we'll use G of S equals 1 over S times S plus 5. We arbitrarily chose 10 and 100 for our values to provide a significant improvement in the phase lead, which is shown in the next slide. So here we can see the uncompensated lead in blue and the compensated lead in the dotted red. You can see that the dotted red starts at a higher magnitude of gain and also has a different behavior in the phase plot. So a phase lag compensator works in pretty much the same way, except it's just in a lagging configuration, and it's used to improve low frequency gains of systems and effectively increasing the steady state accuracy while having little effect on the phase margin. The formula is D of S equals S plus Z over S plus P, assuming that P is much greater than Z. To calculate it, we determine the desired steady state error, we place the poles in zeros, and then we choose K. So we'll use the same equation again, with the same arbitrary values, 10 and 100. And then we find g of s times d of s, which is shown there. And we can see that the behavior of the transfer function is different. We can see that, especially in the phase plot, that there's different behavior around the omega. A phase lead lag compensator is just a combination of both lead and lag compensators, and is used to achieve the benefits of both of these. The formula is shown in that box there. And to calculate it, you design the lead compensator to increase the phase margin and bandwidth. Then we design the lag compensator to improve the steady state accuracy. And then we combine these two compensators in one system to achieve both goals. So we can see that we're using the same formula as in the previous slides. And it's just that this final equation here is just the same, but with the original transfer function. And here is the uncompensated and compensated graphs. The Nyquist stability criterion is a graphical method which is used to determine the stability of a feedback system based on its open loop frequency response. Basically, it provides a way to analyze the stability of a system by plotting the Nyquist plot of its open loop transfer function. The Nyquist plots the map. The plot maps the behavior in the open loop configuration over the complex plane over a variant frequency range. There's a stability rule which says that the stability is determined by counting the number of encirclements of this plot around -1 plus J0 in the complex plane. If n number of unstable poles exists, the Nyquist plot should encircle -1 plus J0 exactly n times for the system to be stable. So this means that given g of s times h of s, the Nyquist plot is obtained by evaluating g of j omega times h of j omega for all values between -infinity and +infinity. So we'll use the example g of s times h of s equals 1 over s times s plus 2. The poles are at 0 and -2. So we then know that the Nyquist curve, and we then plot the Nyquist curve and then check how many times it encircles -1 plus j0. Since there are no poles in the right half of the plane, the system is stable and does not encircle the point. So here we can see the point is -1 plus J0, and that the Nyquist plot does not encircle it. If it did have unstable points in its equation, for example, if it was s minus 2, then it would have to encircle this point n times. Thank you.